Hello everyone, I'm Dr. Priya Hasan. I teach at the Maulana Azad Urdu University, which is located in Hyderabad, India. And this presentation of mine is about biosignatures on Earth and beyond. Now, biosignatures are basically defined as any characteristic atom, molecule, substance, or attribute that can be used as proof of past or current life. That's a biosignature. And what we know is that till now, to date, we haven't found any biosignatures on any known exoplanet. So now the question is, how does one actually define biosignatures? How do we actually search for it? And what can we actually take as the direct, definite smoking gun kind of bioindicator, which is an indicator of life, right? So the issue about biosignatures is not very simple because, like I'll show you in a short while from now, that through the life of the Earth itself, there has been an evolution of biosignatures, right? And that's basically because there have been climatic variations, vegetation variations, various variations which have been there in the Earth itself for these 4.5 billion years of the Earth. And therefore, if you actually look for it, there's only a quarter of the Earth's past where you could actually detect biosignatures, right? And in other periods, detectable biosignatures, they're there, they could be there, but they're not exactly reliable, and they could be only used to give a statistical likelihood of the estimate of life on Earth. But in principle, they cannot be used as direct indicators of life, right? We also will talk a little bit about, we don't have too much of time, but there is something about habitability experiments in our solar system also, of how we've actually been trying to look for biosignatures on Mars, on Venus, on Jupiter, etc. And how these biosignatures are also, again, they are disputable, right? They needn't be, I mean, most of you all would be aware of the phosphine problem, which was there on Venus, but there's also the problem of methane on Mars. And there are various these indicators. And it's now time that we actually focus on this study of biosignatures for the simple reason that now we've actually reached a space in life where, where even with James Webb, you see that they've actually been able to characterize atmospheres of exoplanets, in the sense get the chemical signatures. And therefore, that would be very important as actually defining where are our biosignatures, etc. So if you look at this plot over here, this is from Kettlinger et al. 2007. You can see that the oxygen concentration itself of the Earth's atmosphere has been varying. So for example, if one was actually looking for oxygen on the Earth as a biosignature, then you can see that the amount of it has been very low till about almost 2.5 billion years, right? And then later on, you have a sudden rise which takes place where you actually increase the amount of oxygen. So you can see that if you were observing the Earth itself through 4.5 gigayears, there's been a big difference in its spectrum. And like I said, this is basically because of variations in time, in temperature, as well as chemical composition of the atmosphere on the Earth. So let's look at the most important vital biosignatures, which are basically water and carbon dioxide. Now, although water and carbon dioxide, they are vital components of life, and they are the unmistakable indicators of it, it is not appropriate for us to use them as biosignatures because, in principle, they were present in the Earth's atmosphere before life actually began to exist there. Now, they can actually be used, water and carbon dioxide, they can actually be used as certain signs of life if the abundance of these molecules is greater than what could have been present before life emerged, right? Now, the other thing is we look at methane, right? So if you look at methane, the abundance of methane from 3.5 to 4 gigayears ago, and the existence of water, carbon dioxide, and oxygen, the visible and thermal infrared regions of the spectrum, these are univocal signs of life, right? This is from the Kettlinger this thing. And typically, like for example, we do it in Mars, the presence of large amount of methane. We've been using that as indicators of life, but the problem is that that doesn't necessarily mean that there's life there, as it may be even a byproduct of atmospheric chemistry or brought about by potential non-biological processes, such as the oxidation of the planet's crust and upper mantle. The same argument applies even for phosphine detection on Venus, where a lot of effort was taken about actually trying to explain the amount of abundance that was found on phosphine to check whether these could be formed by some natural processes, or do you necessarily need life to be present on Venus so that you can actually have this abundance. Now, so if you actually look at it very critically, only in the recent 10% of the solar system's age were the biosignatures of oxygen as well as ozone detectable in the visible and thermal infrared spectrums. And while nitrogen oxide could be discovered in later stages and earlier, methane could be only detected with limited resolution. So if you were actually looking at from space trying to detect life on Earth, you would have not detected it most probably. Chances are high. Now, oxygen and nitrous oxide, these are unmistakable signs of life. But the thing is that oxygen, if you have to detect it, it must be produced synchronously and replenished in order to be detected. The problem is that because oxygen is very chemically reactive, so if it's present in the atmosphere, it will most probably react with something else. So you need some other source which will keep on producing the oxygen so that you have that abundance. Now, oxygen and ozone can be detected in visible and thermal infrared regions of the spectrum. These are signs of photosynthetic biological activity that occurred throughout the solar system's past existence. And it would have, like I said, it would be possible to detect these signs of life only in the last 10% of the solar system's age. Methane also, like we use, which has been used to study life on Mars, this was also detectable only in early Earth, and it would have been found only in the period between 3.5 to zero point 0.8 giga-years ago, while nitrous oxide would be detectable only in the later universe, zero point 0.3 giga-years ago. Another important indicator are the chlorofluorocarbons, CCl2F2 and CCl3F. They are found in the atmosphere of modern Earth in the infrared wave bands, and they are potential biosignatures. But for low resolution spectroscopy, their abundances are actually too low. And therefore, the big problem is that in order to identify biosignatures and determine whether a planet is habitable, it's crucial to know the distance of the planet, its evolutionary stage, as well as its spectral resolution. In the present age of exoplanet research, with the launch of James Webb Telescope, as well as the other extremely large telescopes which are coming out, the TMT, the GMT, the ELT, it's therefore very important for us to actually find out these signatures to good precision so that we could be confident. Another important thing which actually played a role in the case of Venus was the existence of clouds. So if you have a planet on which you have clouds, this is a crucial element which should be taken into account. This is basically because clouds reflect regardless of wavelength, and they could also obscure molecules below them, making spectral lines in thermal, infrared, and visible spectrum appear to be fainter. So in conclusion, I would like to conclude that observations of methane, CO2, and 2O, water, oxygen, ozone, all of these are they would be basically observable in the visible and near infrared parts of the spectrum. These would be very important to actually detect life. But we obviously work needs to be done to work on various models for different types of geology, life, and conditions on planets that may enable us to identify a variety of species or molecular types in the atmosphere to confirm that what we see is not the result of naturally occurring geological processes, but is rather the consequence of life. And therefore, finding life and figuring out what exoplanet surfaces look like would greatly depend upon this. So, thank you.